In this video, we're going to be solving 10 MCQ problems for Forces and Dynamics, Unit 2 of AP Physics 1. And if you want to follow along, you can go into the description and download the problem set or try them yourself. So we have a block of mass m that rests on top of a mass of 3m, and the lower block rests on a frictionless horizontal surface. A horizontal force F is applied to the lower block. The coefficient of the static friction between the two blocks is mu s. We want to find the force for which the top block does not slip relative to the lower block. So we know we can think of this entire block system as just one, which means that we just have a consideration of just a collective mass. So we're going to take our m and our 3m, and we have 4m as our mass of our system. So now we're going to use Newton's second law for the entire system. We know that F is equal to ma, which is 4m times a. So rearranging for acceleration, that's F over 4m. So we know that in order for the top block to move with the bottom block, friction has to be accelerating the top block. So let's do Newton's second law for the top block here, because we're going to have a force of friction as well. So we have the summation of our forces is equal to mass times acceleration. Now, the only horizontal force that is acting on the top block is a static friction that is going to be pointing this way. So you have that your static friction is equal to your mass times acceleration. Now we can substitute in the acceleration that we have for our entire system, which is acceleration is equal to F over 4 times the mass. So now we can just cancel out one of those m's here. You get that the force of static friction is going to be the total force divided by 4. So we have an expression for our maximum static friction. Fs max is equal to mu s times the normal force that is exerted. And we know that for our top block, just drawing that FBD, we are going to have in the vertical direction normal and in the downward direction gravitational. In the horizontal, we have the Fs, but we have only two forces in the vertical direction. That's how we know that Fn is equal to Fg. So then you can just say mu s times mass times gravity. So now we can just substitute this Fs max, which we are experiencing on this side, into our equation right here. We have that the force static is equal to 4 times, or we have force static is equal to mu s times mg. So then we can just write mu s mg here is equal to F over 4. What we want to isolate is that F, right? So just multiply both sides by 4, and then we just get that the force is equal to option C. Now for a value that is smaller for F than the maximum that is found in question 1, what is the magnitude and the direction of the friction force on the very top block? Well, we know that we had from question 1, we have this entire system that's going to be moving together. So we have the force over 4m. And again, for our top block, we had that the summation of forces x is ma, where we found Fs was equal to ma. So again, if we solve for Fs, we still have m F over 4m, which simplifies down to F over 4. So we know that the top block, if F was smaller than the maximum, it would lag behind, and our bottom block, it would be pulled to the right. So that means that your static friction would pull your block that is on the top to the right. So we would have F over 4 directed in the right direction, because our static friction, our mu s mg, is not automatically equal to Fs. It's only the maximum slipping threshold, which has to be overcome. So we have a block of mass m that rests on a rough incline of angle theta. It is connected by a light string over a frictionless pulley to a hanging block of mass m, and the system is released from rest. So the coefficient of friction between the block and the incline is mu k. Assume that the mass is large enough that the hanging block accelerates in the downward direction. So what we have is, for the hanging mass, we're going to make our downward direction as positive. So for this mass, we have F is equal to ma, and we have mg minus tension is equal to mass times acceleration. Well, we know that for the incline block M, we can also make our upward direction as positive because you're just looking at this like in one consecutive direction. Acceleration is just going in that direction, like that counter or that clockwise direction, I mean. So we have for this side tension up the incline, and we have this negative frictional force, but we also are going to have a force of gravity. We have our Fg here, but we want to break that up into components because you're going to redefine your incline like this. So you have, actually, positive x is going to be in this direction. So you have your mg sine of theta, because this angle will be theta, and then this will be mg cosine theta as a component. You have your normal force acting up. So let's just write out the Newton's equation for this. We have the summation of forces, ma, and this is going to be block big M, A. So we have tension minus mg sine of the angle theta minus the force of friction is equal to mass acceleration. Our normal force on the incline, Fn, is equal to mg cosine theta, because in the vertical direction, those are the only forces that we have acting. So you also have an acceleration that's equal to 0 in the vertical direction, because we only have that horizontal acceleration movement. Now, back to this first equation, we can see that Fk, we can rewrite as mu k times your normal force for ma. So that's this thing right here. So that's tension minus mg sine of theta. So you can rewrite that as mu k times mg cosine of theta is equal to mass acceleration. So that's tension minus mg sine of theta plus mg sine of theta. Okay, so yeah, you also have mu k right here. So now after this, we can take our two Newton's equations. We have over here mg minus t is equal to ma as our first equation, and we have this second equation right here, which we'll call equation 2. Now let's take them together. So we have mg minus big mg sine of theta minus mu k mg cosine of the angle theta is equal to your system mass. It's important. You have to have this as your entire system's mass, m plus big M times the acceleration of your system, because we're considering everything all together at this point. So this just is going to simplify to acceleration, and you're going to divide everything by your total mass of your system. You can divide this by m plus big M, and that cancels out. So let's just write our whole entire answer again. We have mg minus mg sine angle theta minus mu k mg cosine of the angle theta, all divided by your collective mass m plus m. So that is your answer right there. Now, just to backtrack, this is what we took. We had that mg minus t, and we also had this t minus mg sine of theta. So then we took all of that and we just added those, and then we saw that our tension canceled out, which is how we got this expression here. So that is option A. Now, which expression gives the tension in the string while the system accelerates? Well, when we have our acceleration, it's because we have that block M, and then we had an acceleration downward, so that, or for our hanging mass, while the system accelerates in the string. So let's make mg downward, actually, and let's make our tension force upward. So then in this case, you'd have F is equal to ma, you'd have mg minus t is equal to ma. Solving for tension, subtract that mg, you have negative t is equal to ma minus mg. Then you have tension, dividing both sides by -1 here. So your tension is equal to a negative ma plus an mg. So tension is equal to, factoring out an m, you have a g minus a, or you can also think of it like this, mg minus ma, which is how I did. So then this is how you get your tension definition here. That is option B. So we have, since the mass is going to accelerate down, you have an F net down. Mass accelerates down, your F net is in the downward direction. Therefore, the weight has to be greater than our tension as well. And we have a block that's pushed against a vertical wall by a horizontal force F. The coefficient of static friction between the block and the wall is mu s, and the block remains at rest. What is the minimum value of F that can keep the block from sliding downwards? Well, we have a applied force into the wall right here, and we have that the wall is going to push back with a normal force as well in order to support it from going through the wall. So we know that there is no horizontal acceleration because our v is equal to 0, and we have Fn equal to F in the horizontal direction. So in the vertical direction, though, we have gravity that is going to be pulling down, right, mg there, and you also are going to have an force of friction right here, which is going to be here when you're at the point of contact. It's drawn a little weird, but that is going to be acting upward because it's going to be opposing your gravity. So we can write again that Fs is equal to mu s times normal force, and we know that our normal force is equal to F here, so then just substituting that in, we get that your force of friction is equal to mg times mu s. So then if you take your holding your block, you have mu s is times F is equal to mg. So then solving for F, you just get you get mg over mu s to barely hold the block. So that is what you would have to overcome, because we're using that maximum Fs max condition. So that's option C. So we have a larger horizontal push that creates our normal force here, and because you have that larger push, that is going to give you more static friction that holds the block up. So if you increase your force, then that's going to increase the frictional force because you have an increase in normal force. So yeah, your Fs will also go up. Now for our next question, we have a student of mass m stands on a scale in an elevator. The elevator is moving up but slowing down with an acceleration of magnitude a. What does the scale read? So the scale is going to read your normal force that you have. So let's make our upward direction as positive, which means that on our FBD for a student, we're going to have a normal force upward, and you're going to have an mg that's downward. So if your acceleration is going to be downward, because you have an elevator moving up, but it's slowing down, that means that when you have slowing down acceleration, that means you have an acceleration, but it's being degraded, which means that you're going to have velocity and acceleration pointing in opposite directions. So for example, that would be like if you have an acceleration pointing up and then you had a v pointing down, and when you do that, it's slowly going to decrease. Or for example, if you had an acceleration that is pointing down and you had a velocity that's pointing in the upward direction. So in this case, we know that our acceleration here is going to be down, which means that we have a velocity that is up. So now let's use Newton's second law. We have summation of our forces y is equal to ma times y. So you have a normal force acting up minus your mg, and that's your mass times your negative acceleration. You're going to just add mg to both sides, and you have your normal force is equal to your mg minus your negative ma. So you can just factor out your m here conveniently. You have g minus a, and the scale is going to read option B. So what this is going to do physically for the student is that the student is going to feel lighter because the elevator's acceleration is in the downward direction. So that is describing your change in velocity over time. So your change in velocity over time is just going in that downward direction, so you feel lighter because it's helping you go down. Now we have a block of mass m that is pulled across a rough horizontal surface by a force F applied at an angle theta above the horizontal, and the coefficient of friction is mu k. So what we have is we want to find the block's acceleration in the rightward direction. So first off, we have our normal force acting up, we have our mg acting down at the center of mass, and we have a force that is not at an angle, that is not at the conventional coordinate system of up y, right x. So what we're going to do is actually make that force into something that works on our plane. So then we can split this force into an fx cosine of angle theta, because this is, or we have this. So this is going to be your adjacent side, this is your hypotenuse, and this is your opposite. So this is Fy is equal to your force here. So this is your F cosine of theta. Fx is equal to F cosine of theta. This is F sine of theta. So now what we can do is just sum our vertical and horizontal forces. Upward, we also have a rough horizontal surface, which means we have, at the point of contact, we have the force of friction. So vertically, we have no acceleration because the block is not going to be leaving the table surface, neither is it going through the table surface. We only have a horizontal acceleration. But in our vertical direction, it's equal to 0. So upward, we have the normal force, and downward, upward we have the normal force. We also have upward of F sine of theta, and we also have downward mg, and that's equal to 0. So solving for Fn, we get minus F sine of theta here, plus mg, minus F sine of theta here, plus mg. All that cancels out. You get negative, or we can just say mg minus F sine of theta. So then let's think our friction here. We have Fk, because the block is going to be moving actually. So this is equal to mu k times your normal force. We had our normal force, which was this expression over here, so you can actually substitute this in right here. So this is going to be mg minus F sine of the angle theta. So then if we have our horizontal forces, right, Fx is equal to ma, and that's because ax does not equal to 0. So you have in the positive direction F cosine of theta, the negative direction you have negative Fk is all equal to ma. So then we can substitute Fk that we found earlier. We have that this is F cosine of theta minus mu k times mg times, or minus F sine of angle theta is equal to the mass times acceleration. So acceleration is just equal to F cosine of angle theta minus mu k times mg minus F times sine of the angle theta, all divided by our mass, because we just, over here was just our m that we had to cancel, by the way. So then we got our acceleration like that. So this is going to be option B. And this makes sense because if you pull up, that is going to decrease your normal force because you're providing this Fy right here. Fy is going to aid your Fn. So it's also in the upward direction. If it's in the same direction, you can just add them. So then you have to exert less normal force in order to keep this same movement, or the same position of being on top of the table. So the table has to exert less of a normal force to keep the weight of the block above the table. So, and this is also going to reduce your friction as well, because your friction is, you're going to be slightly lifted up off the table. So that's decreasing your Fk. Now we have a mass of m on a frictionless horizontal track that is connected by a light string over a frictionless pulley to a hanging mass m, and the cart is pulled to the right by a horizontal force F while the hanging mass accelerates upward. So your hanging mass is accelerated in the upward direction. Well, we're going to make the cart's motion to the right as positive, or the cart is pulled to the right. Okay. So for big M, we have horizontally the force of F, and then we have tension to the right, or to the left. So for the hanging mass, we have a tension that is going to be up, and we have mg that is going to be down. So let's write the Newton's law here. We have F minus T is equal to ma, and here we have T minus mg is equal to ma. Now, let's add our equations together. This is going to be equation 1, and this is going to be equation 2. 1 plus 2. So let's line them up. We have F minus T is equal to big ma, and we have T minus mg is equal to ma. So you can see that tension's just canceling out. You get F minus mg is equal to ma plus ma, where you can factor out acceleration, and you get m plus m. F is minus mg, and then you just get here dividing both sides by m plus m, and this one by m plus m. Acceleration is equal to force minus mass gravity over m plus m, which is option A. So your Fa is going to drive your system, and the mass of the hanging, the weight, is going to oppose your upward motion. So we have a block that slides down a rough incline at a constant speed, and the incline angle is theta. The coefficient of friction is mu k. Which of the following relations have to be true? So if you have constant speed, again, acceleration is equal to 0. So that means that F net on the incline, or acting on the incline, is going to be equal to 0 because F ma. So let's break down our components here. You have a downward direction of force gravity. Breaking into components, you have mg sine theta, and you have mg cosine of theta. So normal, we have Fn. So let's write our friction here. We're going up, or it's sliding, never mind, it's sliding downward a rough incline at a constant speed. So actually this Fk should be that way, but we have mg sine of theta minus Fk is equal to 0. So mg sine of theta is equal to Fk. So your normal force is equal to mg cosine of angle theta. So if you have your kinetic friction, that is equal to mu k Fn, and this is going to be Fn is mg cosine theta. So you have Fk is mu k times mg cosine of theta. If you substitute that in here, you have mg sine of theta is equal to our mu k mg cosine of theta. So in this case, you can cancel out your mg's on both sides. You get your sine theta is equal to mu k of cosine of angle theta. So then all you can do is just cancel by cosine theta here, and you know that mu k is equal to tangent theta because this whole entire expression is equal to tan theta. So that's just simplifying things down. Answer A. So if you have a constant V, that means that your gravity component is going to be balanced by your kinetic friction. So that's why Fk is equal to mg sine of theta right here. They balance. And that is why you have a constant V right there. So you have two students that pull on a rope using two ropes. Student 1 pulls with a force F to the east, and you have rope 2 that pulls with 2F at an angle of 60 degrees north of the west. So you have a third student that pulls on a rope so that the ring remains at rest. So how would we even do this? Well, let's start off with making our eastward direction as positive and our northward direction as positive as well. So let's make rope 1. This is directly on 0 degrees, so that is a vector. That's just going to be F0. Now for this second one, we have 2F, and then this is 60 degrees north of west. So if the x component is to the west, we can actually break this up. We have f2x. This would be negative 2f times cosine the angle of 60 degrees. So that would be theta, right? So this is your adjacent, that's your hypotenuse. This is your opposite. Now, this is all just equal to 60 cosine of theta is 1/2. So this is negative 2f, and you get negative f is equal to f2x. Now, what about its vertical component? Well, upward we have f2y is equal to 2f sine of the angle 60 degrees. That was theta. So then you have 2f times the root of 3 over 2. And you can cancel out that 2. You have f times the root of 3, or root 3 times f. So that's f2y. So in order for the ring to remain at rest, you have to have the third rope pulled south with the same magnitude, because we only have this vertical force acting. We have no other vertical forces acting. We only have these two horizontal forces. So if we have summation of forces in x, we have f plus or minus f2x. So that's equals to 0. Now in the vertical direction, you have fy. That also has to equal to 0 to remain at rest. So upward you have f2y. So then in the downward direction, you must have something that is negative f2y, right? Something with the same magnitude but the opposite direction, which is option C. So the east and west components, they cancel. So you only have this net force that is upward. So you need something to cancel out and exactly balance that force.